Hello. That's good. Looks like the recording has started. Today, I'm going to give myself a challenge to do something I have never done before. I want to try if I can energy model a building in 30 minutes. This is something I have been thinking about for a while, basically since I got a chance to roll the Homestar design guideline with my colleagues from my previous job. Saying that, it actually took about 2 years for me to do that. So it's better late than never. For those who don't know me, I'm Arthur. I have been involving in high performance buildings since the start of my careers around 8 years ago. And since then, I managed to become a passive house designer, Homestar assessor, and all that experience, give or take, lead to my current role as the sustainability and design manager at Queenstown Lakes Community Housing Trust. So the purpose of this challenge, other than just a challenge for myself, is also here to basically show the potential of energy model for other people who have just learned how to energy model or have been considering whether to learn it or not. And hopefully this will give everyone some confidence that an energy modeling is not something that's far-reaching. It can actually be done in quite a short time once you are familiar with it. So, without wasting too much of my precious 30 minutes, let's begin the process. Hopefully it doesn't get too chaotic, given I need to model and try to explain a little bit of what I do at the same time. So, for those who are or have heard of Homestar and New Zealand Green Building Council, you might have heard of the ECCHO tool, which is probably one of the best energy modeling software in New Zealand in terms of practicality, accuracy, and just the usefulness of its functions. So for this demonstration, I am not going to use any of my template resources, just so I'm not cheating. So yeah, myself is based in Queenstown, and this particular house is designed in Queenstown as well. So I'm just going to pretend I am the client. So now I'm starting a new project. And once I have a new project, I need to add a dwelling under this project because sometimes there might be multiple dwellings under one project. So address, skip that. So immediately I come to this required input that's called the CFA, the condition floor area. So immediately I know I need to go back to the drawing to measure. So unfortunately, this is something I cannot skip because the condition floor area is one of the most fundamental entry in any energy model. And obviously, I need to understand how high the building is above sea level and the orientation of that. So luckily, I'm the designer of this house, so hopefully I'm fairly familiar with all of these numbers I need. So with the BIM model, I can easily measure the floor area. And in this case, I need to highlight the floor area is and should be the area of the thermal envelope, not the total building footprint. So in this particular case, I do need to exclude the garage. So now this is the gross floor area. And what we need is the conditioned floor area. So according to the convention of the Homestar technical manual, the condition floor area is basically everything minus the thickness of the external walls. So in this case, I know the condition floor area is 87.4 square meters. So in this case, I'll type in 87.4. And to get the height from sea level, I'll go to Google Earth. So remember, normally when we do an energy model, there is no site plan. It's totally on a conceptual level. So that's why I'm not trying to go to my site plan to source the data above sea level. So I know this is roughly where this new house will be. So on Google Earth, on the bottom right corner, I can now see the height above sea level will be 329 meters. Oh, I've got another number I need. Oh. And okay, the last entry here to define the fundamental thing about the dwelling is the amount of thermal mass. So in this case, it's quite easy. I know there is a concrete slab. I know this is a single-story house. So concrete slab, single-story timber. Right, now I have the dwellings. It's probably a good time to have an overview, like what everything I need to complete my energy model. So firstly, I need to define some assemblies. That's my floor, wall, and roof. And then I need to enter the areas of the floor, wall, and roof from based on my drawings. And then I need to define the thermal bridge and then enter basically all the windows and door, and then choose what ventilation I have. And for this purpose, I'm going to start the model based on the building code H1 minimum specifications. And then maybe on the next video, I can show how I analyze the result and then how we improve from there. So now I do need to add some floor, wall, and roof. So let me start with an easy one. That's the wall. So I'm just going to call it wall 1. And then since we always have a ventilated drain cavity, so it's adjacent to ventilated instead of outdoor. So the main layer will be my 140 framing and insulation. So the main layer will basically be insulation, and in this case, I did say I want to start with building code minimum. So let me start with something like R2.8 insulation, and then I need to define a second layer, which is my timber. Timber, softwood, pine, 12% moisture content. And I'm just going to use the convention of 30% timber content as per New Zealand industry's default. And the building code only requires 90 framing at minimum, and then another 10 millimeter of plasterboard. So now that's pretty much the wall. And as you can see, the actual R value based on 30% timber will only give us R 1.91. So technically is even lower than the minimum required by the building code. But anyway, this is why we do energy model, right? Instead of following the prescribed values. I'm just going to save and return. Then the next easy one will be the roof. So again, roof 1. Roof, again, ventilated because it's over a ventilated roofing and purlin cavity. And this might even be easier. So again, I need to enter a layer of insulation. So in this case, according to the schedule method, from H1, we need something like R7, or I should say R6.6 as the construction R value. So we need something like R7. So in this case, I actually can't find an R7 roof insulation. So I'm just going to override the actual thermal property a little bit to make it R7. So in this case, I'm just going to assume the thermal conductivity as 0.04 and the thickness 280 millimeters. That gives us exactly R7. And again, I need to add some timbers because the insulation is only placed between trusses. So in this case, I'm going to assume 15% timber content instead of 30% like the wall, because in this case, we don't have duets, and also typically trusses is placed at 900 centers instead of 400 or 450. So now, obviously, we have another 2 layers. So one is the battens, ceiling battens, and then another plasterboard. So for that ceiling cavity, I'm just going to add 40 millimeter of air, basically. And then again, there will be some timber in between. And given this layer is so thin, I'm not going to calculate that in great detail. So just assume 15% timber content again, and then 13 millimeter of plasterboard. So now I've got a detailed roof assembly. So like you say here, even if I have R7 of roof insulation, but at the end, it only give me R5.86 as the construction R value. But again, it is kind of what it is. We know what is commonly accepted as compliant, often under-deliver a little bit. I'm going to save and return. And for the floor, in this case, if it's building code minimum requirements, then I will, it's likely to be a rib raft system. So in this case, given the actual insulation is the average between the insulation itself and the concrete ribs, it's quite technical to calculate with accuracy with the tools. So I'm going straight to the first concrete calculator and then find out the exact R value the rib raft can give us. So climate zone 4, I don't have brick, I have 90 framing, 20 parts, and the areas now will be 87 square meters, and the perimeter of the slab. So again, I need to go back to my model and then measure the perimeter of the slab. So give or take 46 linear meters. So 46. And I have 90 framing. And part of the perimeter has no edge insulation. Yes, I do have an internal garage here. So now I have 10 meters of this slab that's basically uninsulated. So next. So now this first calculator gives me the exact R value of the total slab to be 2.05. So in ECCHO, we can add a custom assembly, floor 1 in this case, and then I can enter the exact R value. Now I have all the floors and wall and roof I need. I just need to link that with the actual area of this particular house. So the beauty of modeling simple houses is I kind of know a lot of the perimeter already without referring to sections or even details. So in this case, for example, I know the stud height is 2.4, probably 2.45 in reality. And then the thickness of the roof insulation is 280, or I can round it up to 300. And if I use a typical riprap, the thickness of the slab is also 300. So to simplify things, especially in this conceptual stage, in the early stage of the project, I'm just going to assume my wall height measured to the external corner is exactly 3 meters. So all I need is to measure some linear meters. So in this case, my north wall is 14.5. External wall is 14.5 times 3 meters. Then the assembly is wall 1, and then it's north, so it's 0, no deviation from north. So now I have 3 east-facing walls, 1, 2, 3. So the first one, 3.1 meters, then 1.7, then 3.6. And east facing, so the deviation from north is 90 degrees. It's the second east facing wall. Last one. Then I need a south facing wall. So I have again 3 south facing walls. First one is 900, and then 6.4, 7.2. Then the south facing, so the deviation from north is 180 degrees. And then I only have one west facing wall. That's 8.4 meters. It's 270. Yeah, so that's all my wall entries. Now I can move on to 4. 4 to outside. And then whenever there is irregular shape of slab and roofs, we normally can simplify the entry even more, but before that, we just need to measure the exact area somewhere else. So in this case, the exact area is 94.2 square meters. So we can just do 94.2 times 1. So this will give us exactly 94.2 square meters of floor. And then in this case, because the ceiling is all flat ceiling, so I know the roof area will be exact the same. And I just need to pick the right assemblies. And because again, it's flat roof, so it doesn't matter whether it's facing anyway, because when it's flat, there's essentially no orientation. We just put 0 here. Yeah, so now that's all my floor, wall, and roofs. And in terms of thermal bridges, yes, if we follow Homestar convention, we do need to pick a thermal bridge. So in this case, most of the built-in thermal bridges come from the HPCD handbook. So I do need to go to the HPCD handbook to see which one is the most relevant one. So I think the perimeter slab detail starts from 25. And I just need to pick the closest one and use that number. So in this case, it's on insulated slabs. So we can skip that. And there's no slab edge insulation here. So again, skip that. Oh, here we go. This looks very, very close to the rib raft detail with just a little bit of slab edge insulation and then the pots. So yeah, raft slab. One caveat is this layer may not be the waffle slab. So let me just go down and check a few more details to see if there is a more relevant one. Yeah, so for example, this detail, it shows the actual waffle slab, but obviously this is not relevant because there is no insulation anywhere else. Hopefully I can find one. So again, this is good to some degree, but the whole construction is just too different. For example, the wall. So I can't use this one either. Right, looks like there is no exact match from the existing detail library we have. So in this case, I just need to pick the closest one for now. So in this case, this will be detail 28. So I'll go back to ECCHO and pick detail 28. So I have previously measured the perimeter length of the slab is 46 meters. And in this case, it's the ground perimeter thermal bridge. So I just need to save. So the next step, which can be the most time-consuming one, is to enter all the windows and doors. And for the sake of speed, I'm going to enter one window as one window. For those who have done the Homestar course, you may remember that if we want to do that 100% or more accurately, we should enter one sash as one window. But for this purpose, in this early stage, I'm just going to enter the whole window as one window. And there is actually one benefit here. If I will enter the whole window as one window, that means I overestimate glazing and underestimate the frame. That means I kind of overestimate the overheating a little bit if that's the case. So there is some benefit there, but I just need to be a little bit mindful that I have made such assumption. So again, in this case, because I am the designer for this house, so I understand all the sizes of the window very well. So I know all these 5 windows are exact the same size. That also mean all the north-facing windows, I can just enter it once. And then multiply the quantity by 4. So source data calculated from glazing and frame area, that's correct. And then I need to select a double glazing. So essentially, if you don't know the exact double glazing, there are some built-in data within ECCHO. So for example, this one with U value 1.1 is probably fairly close to what the market default is nowadays. So I'm just going to use that for now. And again, in Queenstown, I will start with thermally broken window, but it's not installed in the recessed position. So they are installed on the north wall, and then there are 4 of them. The width in meters is 1.8 by 1.2. And in terms of the shading, so shading is like a little bit of art, right? Because how do you suddenly just guesstimate the shading out of nowhere? And that's why in the Homestar design guide, we have done a lot of work in the background to make those shading assumptions easier and more realistic to make. So you can find that resource under the overheating chapter. So in this case, there is some tables and examples for you to work out semi-realistic percentage of shading. So let me see. So firstly, side shading. Houses or multi-unit dwellings in a neighborhood with similar types of housing next door. So winter, summer, 80%, 90%, and I believe this might be the default where those numbers in ECCHO came from. And in this case, I'm just going to check the example. Yeah, that kind of houses within similar lower density neighborhood, it does look like is our case. And then we need to consider whether there is any self-shading for this house. And in this case, because all the windows are on the walls with no wing wall, no corners, so it's basically a box form. And obviously there is some recesses, but basically there is no window anywhere around here. So we can consider there is no self-shading by the building itself. That means it's 100%. The box form is not L-shaped. So yeah, looks like in this case, we can definitely use 80%, 90% to start with. In the Homestar Guide, it does give us some flexibility to use blinds and curtains, but I'm not going there for now. So yeah, knowing this, and then in this case, there is basically no overhang unless I want to count some flashings, which is probably too details for this stage. So that will be my first window, and then the next window will be, again, another one, the same size. And that's on the west. That's it. Then I need to enter this sliding door. So unless we know there is a specific brand or specific suite of windows or doors, otherwise we, in ECCHO, we're actually encouraged to use those generic data to make it about right, and also at the same time avoid mistakes, including typing mistakes when sometimes if we want to define our own things. So in this case, I do want to enter the sliding door as per mullion because it's a big window, it's a big door, so the impact can be quite a bit. That's kind of my own judgment. So in this case, the total width is 2.7 meters, so times 2, so each pan is 1.35 meters. Yeah, so that's my sliding door, quantity 2. Yeah. Now, south windows. So this one, the size is 800 by 1.2. The other one is 600 by 1.2. There is also one very useful function. I can, for similar windows, I can actually just copy it instead of defining that from scratch. And also now we have the live editing, which means I can change any parameters directly on the screen. Handy. Oh, this is south-facing windows. And don't remember, or don't forget, just say don't forget to enter the door between the hallway and the garage, because that's part of the thermal envelope as well. So in this case, so in this case, it's obviously a solid door panel. So say if it's a hollow core timber door panel, then, well, I guess it should be considered as a standard door. I don't actually know whether that's R0.5, but given that's the only choice I have now, then I'm going to select it anyway. And framing type, in this case, it's also timber, generic timber. Yeah, should be good enough. And again, link to the wall, and then enter the width and height. In this case, because it's facing the garage, so it's permanently shaded, we can't use the 80%, 90% anymore. It's permanently shaded. Right, so I'll create this door. Lastly, I have the front door and this additional window to enter. So this one, 1.3, it's a side light. So I'll enter the side light first. So this would be east 2 width. So let's assume the front door is 1 meter by 2.2. And then now there is an overhang we need to consider. So the shading depth will be 0.9, and then the shading height, that's the distance from the top of the window to the soffit in this case. So by 0.1, give or take, because the soffit is right at the window head. Oh, by the way, so if in this case the front door panel is not a glass, so I can't use that. I need to use, again, I'll use the standard door, R0.5. Correct. Yeah, just copy this. Now the side light is only 30 centimeters wide, and everything else should be the same. So lastly, just need to copy another window. And now this is on the east wall. And then the height is only 0.6 meters. So it's a high level slot window. So now I have entered all the windows and estimated all the shadings essentially. So that by this point, the energy model is 90% finished. There will be a few more buttons to click. For example, I need to pick a ventilation. So in this case, if it's building code, there will not be any proper ventilation system. So it's just intermittent kitchen and bathroom extractor fan, and then some opening windows, and that's it. So yeah, so basically select that. And then in terms of some additional summer ventilation through opening windows to reduce overheating, we can count out some of that. So For example, I know every room has a 600 wide awning window. So say if we allow a pair to open during occupied hours, and then we allow these two in the bathrooms to open to create some cross ventilation, I don't think that's an unrealistic assumption. So I'm just going to enter the total opening width on each side at 1.2. And then the opening height, if it's awning, then if it opens like 30°, then it will probably open, I don't know, 30 centimeters. So I don't want to overcount it. I'm just going to assume it's 30 centimeters. And I'll assume these windows can be open whenever there is people in the room. So now you can see the overheating drop a little bit. So yeah, as soon as we select the ventilation, the energy model is pretty much done. But if I want to put some cherries on the cake to make it even more complete, I can enter some heating systems, because I know the industry default, everyone has a heat pump nowadays. So let me assume there is a heat pump. And then an average COP of a heat pump, I can probably assume something like 3.5, which means 350% more efficient. And this heat pump will contribute 50% of the heating, and the rest is covered by individual panel heaters in the bedrooms. So again, that's a reasonable assumption. And hot water system, so there is a hot water cylinder, for example, and obviously the hot water cylinder can contribute a little bit to the overheating situation. So in this case, it comes with a bit of default already, so that's good. ECCHO currently assumes there is a 180-liter hot water cylinder inside the thermal envelope, which contributes some overheating. So for 4-bedroom house, we probably need something like 270-liter. And in this case, I guess most people will probably have the hot water cylinder in the garage. So I'll actually assume that's outside the thermal envelope. And this might actually help with the overheating a little bit. Yeah, as expected. Yeah, so by this point, we can already go to the result and see the preliminary result of this energy model. So yeah, look at some of those beautiful numbers. Annual heating demand, 142, which by my previous energy modeling experience with many like houses that's modeled to the legal minimum standard, 142 is kind of neither good or bad. And that kind of reflects part of the quality of the passive solar design. It obviously has some room to be further improved, but it's also not bad already. And on the right-hand side, there is this heat demand chart. So you can see there is quite a consistent heat loss through the window, ventilation, floor, and external walls. And obviously, there is some solar gain to compensate that, but nowhere close to covering the heating demand, which is still quite massive. So I think I failed the challenge a little bit by probably 5 minutes, but overall, I'm happy with the result. So here we go. This is how we can energy model a house that as a designer in just over 30 minutes. And this won't be the only video I try to record. The next video, I want to show everyone how we spend another 30 minutes to analyze the result and then create some improvements and make some informed decision out of this process. But that's it for today. Thanks. Until next time.